And I think I finally arrived at a complete new interpretation of quantum mechanics. You know that when you have a theory of the world, like quantum mechanics, it's not enough to have just a good mathematical formulation. You must have also a story that you are able to tell about it that is free of mathematics. Because the mathematics cannot tell you what questions to ask it. It can answer any question you ask, but it cannot tell you what are the interesting questions to ask. In order to know what interesting questions to ask, you must have a way to understand what the theory means, not in mathematical terms, but a new kind of intuition or story you can tell about it that will be as much as possible free of mathematics. That story, if it's correct, can help you to see things in the mathematics that otherwise you wouldn't have been able to see. So that is the importance of good interpretation. So the first step is to show that the kind of story that everybody is telling about quantum mechanics is completely wrong. I will tell you the type of story that people usually tell about quantum mechanics. They say the following thing. First of all, they say that contrary to classical physics, the quantum world is not deterministic. That means that even if we know everything that we can know about a given system, like an atom, for example, we cannot predict when it will decay and emit a photon. One atom will emit the photon after 1 second, and the other atom, which is completely identical, and it has exactly the same surrounding, will emit the photon after an hour for no reason at all. So that is the thing that made Einstein completely angry. He said, I don't believe that God plays dice. I don't believe that nature is capricious or unreasonable, because we always thought in science that everything that happens must have a reason. And here, for no reason at all, one atom behaves one way and the other another way. So people say about quantum mechanics, we simply have to accept it, that the world is non-deterministic for no reason at all. We just have to take it as an axiom. And my first point is that it's not true. In fact, we can show that just because nature is not deterministic, it allows the system, the quantum system, to have properties that it could not have if nature was deterministic. So there is a reason for this indeterminism, as I will describe. And once you find a reason for it, then it's not anymore that nature is capricious. It does it for a given reason. So that's the first thing that is wrong, what people tell us about quantum mechanics, that for no reason at all, the world is not deterministic. There is a reason for it. The next thing we are told about quantum mechanics or quantum domain is that every measurement that we do on a quantum system necessarily disturb it so much that we cannot say that what we saw what was there before, because really most of what you see is because of the way that we disturb it. So that is completely wrong again. I have discovered a new kind of measurement that I call non-disturbing measurements or weak measurements that don't disturb the system at all and nevertheless tell us all the information that we need about the system, provided we can have many examples that we can test. So we will discuss it more carefully, but the idea is that it's not true that there is no reality in the quantum domain. There is a reality, but in order to find it, you have to do the right measurement that don't disturb this reality. Okay? That's the next thing. The last most important thing about we are told about quantum mechanics, which is wrong, is that a quantum particle, like electron, can be either a particle or a wave. They say that the electron, for example, in hydrogen atom is like a wave surrounding the proton, not a particle rotating around the proton, but a wave surrounding. So we think about quantum particles as if they are classical light waves. But classical wave has a property that if you look at one point on the intensity of this wave, you don't change the wave at other places. But the wave of the electron has the property that if you look at one point and find the electron there, the whole wave disappears magically and is left only at the place where you found the electron. Now, that is an illogical behavior because if a moment before the charge of the electron and the mass of the electron were spread all over the wave, and then you finally find it in one place, then all these charge masses collapse very quickly to this point. That will create a lot of radiation and disturbance that you never see. So that is not the right description. On the other hand, people say, but look, it must be a wave because there is no other way to understand why we see interference on the individual electron. For example, you take an electron and send it through a screen that has two open slits. And if only one of the slits is open and later you put a photographic plate and collect one electron after the other, you see the pattern that's called diffraction pattern. You see a spread of points of wave that came from one slit. If the other slit is open, you see the wave that came from the other slit. But if you open both slits, each electron that comes must go through both of them in order to explain that you wrote destructive interference, that there are points on the photographic stream that suddenly no electron appear there if the two slits are open. But if only one slit is open, any of them, it will appear there. So people say because of that, there is no way to understand the behavior, and it will say that the electron also can be a wave. And I will show again that that is not true by doing the kind of new experiment that I'm talking about. I can see the interference pattern, and nevertheless, afterward, I can do a measurement that will tell me through which slit the particle went. So you must have another explanation for interference, not by waves. And I found that interpretation. In fact, I found that interpretation of this new behavior already in the 60s. In 1964, I came to Munich and I visited Max Planck Institute. And I was introduced to Heisenberg, who was alive then. Yes, few more years after that, he was alive. And then when I entered to his room and we were introduced, I asked Professor Heisenberg, do you know how to explain interference in your language? Because the language of Heisenberg was a language that was still used of position and momentum and the dynamics, new dynamics that correspond to matrices instead of usual variables. So there was the dynamics that's called non-commuting dynamics. So anyhow, I asked him, your dynamics, do you know how to explain the interference? He said he doesn't know. So I showed him my new way to think about it. And he got so excited. And from then on, anyone that came to visit him, I was told by his assistant, Peter Du, that the first thing he would take him to a blackboard and show him how to understand the interference in his picture. So the way that I think about interference is by showing that in quantum mechanics, there are the basic equations of motion, or Heisenberg equations of motion, are non-local. The electron, even though it moves at one point, has another variable that will tell the electron later where they appear on the photographic plate. And that variable has non-local equations of motion. So although the electron goes through one slit, that variable knows that the other slit is open or not because there are non-local equations of motion. And at first you think if there are non-local equations of motion, something terrible can happen because it will destroy causality. The particle goes through one slit, you open the other slit, and instantaneously that variable knows that the other slit is opened. So that way that quantum mechanics gets out of this problem is by having the uncertainties that if you know from the past through which field the particle goes, that variable that has the non-local equation of motion is completely uncertain. But if you use pre- and post-selection, you can prepare initially the particle that you don't know through which field it goes. You then check the interference pattern by looking on it with big measurements and do this on ensemble, so you don't disturb any of the particles. And then after you see that interference by big measurement, you can check through which field the particle went.
I don't usually stop mid-conversation to talk about sleep, but I've been using something that's made an appreciable difference. It's called Evening Being by Verso. Now, if you're like me, getting quality sleep while juggling work and stress and everything else isn't exactly straightforward. I've tried various routines. By the way, I have my sleep hygiene on point, like avoiding screens, for instance, after a certain time and don't eat after a certain time. But sometimes the stress accumulates. It does this for all of us, and deep sleep gets harder. Evening Being uses research-backed ingredients that help your body calm an active mind. This formula is melatonin-free, by the way, which means there's no dependencies or morning grogginess. I know some people get that. This formula also helps improve deep and REM sleep cycles and supports staying asleep longer. Basically, it tells your body to relax and to wake less. Since taking it, I and my wife have noticed that we've fallen asleep faster, so sleep latency is lower. I also feel more refreshed, my energy is distinctly more stable throughout the day, and I'm discernibly quicker mentally. I haven't changed anything else about my supplement regimen. I've just added this to my nighttime routine, and it's helped me sleep consistently without forcing it. Something else to note is that Verso third-party tests every batch and publishes the results. This matters to me personally because I want to know exactly what I'm getting. If you're looking to dial in your sleep quality and recovery and wake up actually rested, then check it out. Head to evening.ver.so/TOE and use the code TOE to get 15% off your first order. That's evening.ver.so/TOE. Again, the code is TOE. Thanks to Verso for sponsoring this episode.